Dear listener, today we listen about quantum physics laws and principles, so listen start to end carefully. Thanks. Quantum physics laws and principles. Quantum physics, also known as quantum mechanics, is a fundamental branch of physics that describes the behavior of matter and energy on the atomic and subatomic scales. It defies classical intuition and introduces principles that challenge our everyday understanding of reality. The foundation of quantum mechanics is based on several key concepts such as wave-particle duality, superposition, the uncertainty principle, quantization, and quantum entanglement. These principles are supported by mathematical formulations and experimental evidence, making them essential for modern physics and technology. Wave-particle duality. Wave-particle duality, proposed by Louis de Broglie, is a fundamental concept of quantum mechanics that states that all particles exhibit both wave-like and particle-like behavior. This dual nature is dependent on how the particle is observed. For example, light behaves as a wave when it undergoes diffraction and interference, as seen in the double-slit experiment. Light also behaves as a particle photon when it interacts with matter, as demonstrated in the photoelectric effect, explained by Albert Einstein. Similarly, electrons, which were traditionally considered particles, exhibit wave-like properties such as diffraction and interference when passed through a crystal or double-slit apparatus. This principle underlies the operation of electron microscopes and quantum wave functions. Superposition principle. Superposition is one of the most intriguing aspects of quantum mechanics. It states that a quantum system can exist in multiple states simultaneously until a measurement collapses the system into a definite state. For example, an electron in an atom does not orbit the nucleus in a single, defined path but exists in a cloud of probabilities described by its wave function. Schrödinger's cat thought experiment illustrates superposition by presenting a cat that is simultaneously alive and dead until observed. This principle is fundamental to quantum computing, where qubits can exist in a superposition of 0 and 1, enabling immense computational power compared to classical bits. Heisenberg's uncertainty principle. Werner Heisenberg formulated the uncertainty principle, which states that it is impossible to simultaneously know both the exact position and momentum of a particle. Mathematically, it is expressed as, where is the uncertainty in position, is the uncertainty in momentum, and is the reduced Planck's constant. This principle implies that the more precisely we measure a particle's position, the less precisely we can determine its momentum, and vice versa. This uncertainty is not due to measurement errors but is an inherent property of quantum systems. It has profound implications for microscopic particles and influences the behavior of electrons in atoms. Quantization of energy. Quantization is the concept that certain properties, such as energy, can only take discrete values rather than a continuous range. This idea was introduced by Max Planck in his explanation of blackbody radiation and further developed by Niels Bohr in his atomic model. Examples include: electrons in atoms occupy discrete energy levels, they do not exist between these levels. When an electron transitions between energy levels, it absorbs or emits photons with specific quantized energies. This principle explains atomic emission spectra, the stability of atoms, and the development of semiconductor technology. Quantum entanglement. Quantum entanglement describes a phenomenon where two or more particles become correlated in such a way that the state of one particle instantly determines the state of another, regardless of the distance between them. This was famously described by Einstein as spooky action at a distance. Entangled particles exhibit non-local interactions, meaning measuring one immediately affects the other, even if they are separated by vast distances. This principle is foundational to quantum cryptography and quantum teleportation, which are vital for secure communication and future quantum networks. Schrödinger equation, the foundation of quantum mechanics. The Schrödinger equation is a fundamental equation that describes how the quantum state of a system evolves over time. It is expressed as, where is the wave function, is the Hamiltonian operator representing total energy, and is the reduced Planck's constant. This equation provides the probability distribution of a particle's position and energy, forming the basis for quantum mechanics. The role of observation in quantum mechanics. Observation in quantum mechanics plays a crucial role in determining the state of a system. Before measurement, a system exists in a superposition of states. When observed, it collapses into a definite state. This is known as wave function collapse. The interpretation of this phenomenon leads to various philosophical debates and theories, such as the Copenhagen interpretation, which states that reality is probabilistic and determined by measurement. The many worlds interpretation, which suggests that all possible outcomes exist in parallel universes. Applications of quantum mechanics. Quantum mechanics is not just a theoretical framework, it has practical applications that have transformed modern technology. Some key applications include, 1. Atomic and molecular physics. Explains atomic structure, chemical bonding, and electron configurations. Provides the foundation for spectroscopy techniques used in material analysis. 2. Semiconductor and electronic devices. Enables the development of transistors, the building blocks of modern computers. Supports the operation of LEDs, lasers, and solar cells. 3. Quantum computing. Utilizes superposition and entanglement to perform computations exponentially faster than classical computers. Promises breakthroughs in cryptography, drug discovery, and complex simulations. 4. Quantum cryptography and secure communications. Quantum key distribution (QKD) ensures ultra-secure encryption that cannot be hacked. Used in secure military and financial transactions. 5. Medical and imaging technologies. MRI magnetic resonance imaging is based on quantum spin properties. PET scans rely on quantum principles of particle-antiparticle annihilation. 6. Quantum teleportation and future technologies. Scientists have successfully demonstrated quantum teleportation of information. Future advancements in quantum mechanics could lead to revolutionary changes in artificial intelligence, space exploration, and energy systems. Conclusion. Quantum mechanics is one of the most fundamental and revolutionary fields of physics. It challenges classical physics with counterintuitive principles like wave-particle duality, superposition, uncertainty, and entanglement. Despite its abstract nature, quantum mechanics has profoundly impacted our understanding of the universe and led to groundbreaking technological advancements. Ongoing research continues to unveil new mysteries, paving the way for future innovations in computation, communication, and beyond. Please like, share and subscribe my channel for support. Thanks from Relax Audiobook.